Thanks for having me at this very interesting and broad-ranging conference. Yeah, sorry, the title maybe doesn't match exactly what I put in the program. So this is a bit more general. In fact, I will talk a little bit about background. So there's a work with Vincenzo Auletta, Diodato Ferraioli, Ashutosh Rai, Giannicola Scarpa from 2016. That's kind of, by our standards, 10 years is ancient, prehistory. And so the reason why I want to talk about this is because we have some new results in joint work with Yaqing Wang and Giannicola Scarpa. This should be out very soon. And so, yeah, I want to start with a kind of a warm-up games. So, I mean, I know this community is very mixed, but the people to do with working with quantum and with entanglement in particular, they will know non-local games. So let's see, okay. So entanglement and non-locality is an ancient topic in quantum physics by now. And so to get into this mood of games, let's review the Clauser-Horn-Shimonu-Holt game. So there's kind of physicists, they think of this as an inequality, a Bell inequality, but there's kind of, we can gamify this. So there are two players, Alice and Bob. They each of them get a random input from the referee. Each has to respond with another bit. So they're called X and Y, A and B. And there is kind of a winning condition. So the referee collects the responses and they win. So the referee declares they win. They play jointly against the referee. So it's a cooperative game. If the XOR of A and B is equal to the product of X and Y. Yeah, so they are correlated if X and Y are X times Y is 0, and they're anti-correlated if X times Y is 1. And okay, so we put this in this Boolean predicate. And so we can interpret this as the payoff function of the players. Well, of course, it's just giving numbers. And so they want to maximize the expectation of this payoff over their choices, which is the probability of winning, right? And so when you think about this, since the distribution of X and Y is given, I said it's uniform, the expected payoff is determined by the so-called behavior. So when you kind of, if we as we are not the players, we are not the referee, we just observe what's going on, we see that they somehow behave according to a conditional distribution of A, B given X, Y. And so the history of physics, kind of, we distinguish these different classes of kind of behaviors. So this is what Bell introduced, the local hidden variable theory. So it's basically a product distribution, and we take a convex hull. So it's Q of lambda is just a probability distribution. Then there is quantum, this kind of, there's a joint state, and then we make local measurements. And then there is no signaling, which is basically just the condition that the choice of Y cannot be detected by Alice observing X and A, and vice versa. And so again, this is this is the literature review. So this is the CHSH paper. This is the 1960s. You basically go through all the local strategies, and you use convexity to realize that this hidden variable doesn't really do anything for your probability. You have to enumerate all the local strategies, and you find, okay, you can win this only in 3/4 with 3/4 probability, which corresponds to 3 out of the 4 possible input pairs XY. And famously, you can beat this with quantum mechanics. If you have a 2-qubit maximum entangled state and do the correct measurements, you get this number here. It's kind of some sort of angle cosine square of pi over 8. It has to do with the angle between the measurement settings. And this is the maximum. And this is associated with the name of Tyrrellson. And then down here, the maximum of no signaling behaviors is 1. They can always win. That's Popescu-Röhrlich, actually. So this is a little bit, so at the same time, it's still in the 80s. So what I want to talk about today, in the time I have, is quantum advantage in games where the players play against each other. That's kind of, the usual sort of game. When we play games, it's usually, each of us is a separate party and we follow some rules to win. And so, yeah, so kind of a starting point is this Muhammad et al. In the PRX already a while ago, they were investigating bridge, the game of bridge, where there's 2 teams of 2 players playing against each other, and they identified a case where there's a specific scenario of play where they can where a team, so two players can exploit CHSH correlation to play better, which without the entanglement, they would have had to communicate. And communication is I mean, there are certain moves in the game that communication is allowed, but kind of other things are basically cheating. But of course, that is still not really what we want, because the quantum advantage is actually between the two players that cooperate. You know, it's the guys within a team. So is there anything beyond this? And this is what I want to tell you today. So I wouldn't be here if the answer went yes, but I need some time to get there. And so this is more or less the outline of the talk. So like we'll have to spend rather little time on each of the points, but we'll see where we get. So I just want to remind you sort of how do we treat a game mathematically, and this goes back to von Neumann, like many things. He wrote a famous book with Oscar Morgenstern, economist, called Games and Game Theory and the Theory of Games and Economic Behavior, and then Nash, who kind of greatly advanced the field. And so the way we look at this is the game has some number n of players, and each of them has a number of strategies. Some sort of, I mean, a strategy, like if you're playing chess, a strategy would be like basically a complete algorithm to respond to every game situation. Yeah, so if you know how to play chess, then sort of in some sense you have that. But of course, it might not be very fixed. So each game, you might have a slightly different algorithm because you don't remember everything correctly. But for simple games, it's very easy to draw up a table where you can have a complete strategy. And so we assume this is a finite set for mathematical reasons, and then there's a payoff function. And so obviously we want conflict, so every player has a different payoff function. And so it's almost an axiom of rationality in economic behavior that the players aim to maximize the expected payoff. It's kind of the winnings, you know, that's how much they win, and so they want to maximize this. And so a mixed strategy, well, okay, a pure strategy is basically a player just choosing one of these A's from the set. A mixed strategy is a probability distribution. So the idea is that the player in the course of the game might randomize over strategies, and this was recognized by von Neumann already, that this can be a useful thing to play well. And I'm sure you all know games where this is the case, where you do need to randomize. If you don't, I tell you one, rock, paper, scissors. If you play a pure strategy, you will always lose, at least against an opponent who figures out which pure strategy you're playing. So Nash equilibrium, this is kind of actually I'm going to the next slide. I want to write this more mathematically. So I liked this language of random variables. So a mixed strategy is basically just a random variable that has a distribution. And a Nash equilibrium in the setting is a bunch of independent random variables. So kind of each player independently making random choices, such that for every player J and every alternative random variable AJ prime, the expected payoff for this player J is larger for the original tuple compared to the expectation when all other players keep playing their strategies, but this player deviates. And so that's the fundamental idea of every notion of equilibrium. It's a description of how all players play, such that if any one player deviates, they cannot gain from this. Even knowing what the others play, the AJ from this list here is already optimal. Okay. And so famously, Nash proved that every game, like in this description that I gave, there's no additional condition. Every game has at least one equilibrium. It's a wonderful theorem, because it means that we can now start looking for that equilibrium. And maybe if there's more than one, try to optimize something. Yeah, so a little remark here. Maybe I should speed up a little bit. A little remark. In zero-sum two-player games, this is what von Neumann introduced and where he sort of led him to the discovery of linear programming duality. This is actually found by linear programming, like I said. And the optimal value of the game is unique. I mean, the optimal strategy is not exactly unique. That's misleading here. But in general games, there are multiple Nash equilibria, and they have different sort of global properties. Should I go through this example? I mean, this is sort of the very simple two-player game that is not zero-sum. and where each player has just two options. It's called the game of chicken. So you can each player has a fast car. They start racing in opposite directions, so that at some point t=1 they will crash unless one of them swerves, and it's called chickening out. And so if you chicken, of course you survive, but you look bad, you know, especially when the other doesn't. And you look even worse if you both don't swerve, because you will crash and maybe die, like this guy here. You know? So you can work out the equilibria. There are actually exactly 3 Nash equilibria, and they are globally different. So if one of them never swerves, if they just do the dare strategy, the opponent has no choice. I mean, you have to swerve, because otherwise you die, and vice versa. So this works for both of them. But if one of them plays a randomized strategy where you chicken with some probability and you dare with some other probability, that's also an equilibrium. And it turns out not only are the outcome expectation values equal, but they're also slightly higher than the average here. Yeah, so the sum is better. So this kind of these global characteristics. You can have larger social welfare. And of course, they accept this probability of 1 over 9 of crashing. So that's maybe still not very good, but that's an equilibrium, at least with those payoffs. I mean, it depends on sort of how afraid you are of crashing and how afraid you are of looking at chicken. This kind of, you know, that's you can play with this game with the parameters quite a lot. So correlated equilibria, this kind of the next phase of the review. So in light of the previous example, one looks for ways to incentivize the players to go for something more advantageous. I'm talking about avoiding the crash and avoiding chickening out both of us, because they basically look both cowards. Yeah, I'm sorry for this example. I mean, I know this is very macho, but that's kind of, I mean, that's really, I mean, you have to have this mindset, or at least you have to know that there are people who have this mindset to understand the payoff matrix. Anyway, so Robert Aumann in the 70s, he came up with this idea of giving advice. So he said, well, I mean, okay, obviously in Nash, the players play independently, but what happens if you have some kind of joint distribution? So we give some kind of advice to the players, and which might be actually the action that they should take, and this would be how they play. So what would be the notion of equilibrium? Well, when you think about it, again, you have to think about, well, now we give them information. We give them already some random variable. So an attempt of deviating is not just replacing it by another independent gender variable. You have to replace it by a function of what you already have. And so this is it. A correlated equilibrium is a bunch of random variables, jointly distributed now, such that for every j and every Markov chain, so this new variable aj prime is in Markov chain relation with aj and all the others. Why? Because player j observes aj, but not the others. And the expected payoff of the original set is larger equal than the expected payoff of the new one. And so, yeah, so we can make, this is kind of this includes Nash equilibrium, but it's a larger set. In fact, it's a convex set. It's a convex polytope in the simplex, if you look at the joint distributions of these variables. So it's non-empty because it contains the Nash equilibria. But it's typically larger than the convex hull of the Nash equilibria, and we can show this in the game of chicken. The obvious thing is we want to avoid this diagonal here, and so we would just like to I hope this is correct. Oh, yeah, okay. No, we don't avoid this one. We just avoid this guy here. Yeah, exactly. So this is a correlated equilibrium. I mean, you have to check it. And so it's a bit like a traffic light, you know, basically. I mean, sort of it gives a signal that shows them like that if one of them chooses the dare strategy, the other one can chicken out and vice versa. And so, yeah, so this gives an expected payoff that is higher than the Nash equilibrium from before, and it's also fairer because they are both. It's also fair like the previous one because they have the same payoff. So that was the idea of the correlated equilibrium in the classical world. It's, like I said, this is from the 70s. It brings in another agent when you think about it, because the players cannot generate those correlations themselves. This has to come from outside. They have to somehow trust it has a certain distribution. So nowadays we would call this maybe like an internet service. And there is a name for this in game theory. They call this like it's an example of a mechanism. So if you modify the gameplay by having access to this correlation, and it suddenly changes the landscape of equilibrium. And yeah, so we come back to linear programming. That if you want to, this C is a convex closed polytope, we can actually optimize some things like the social welfare, like this, which is code name for the sum of all the payoffs. We can optimize such functions by linear programming. So this is actually easy in some sense if the game is not too complex. And so, yeah, quantum correlations, well, okay, I'm really getting in trouble, I guess. The first thing is in these kind of games I described to you, there is no fundamental role for such games because, I mean, whatever well, if you imagine, okay, give a state, well, in the end, they have to play. They need, which means everybody needs to measure. There has to be these local POVMs. And then we get a joint distribution of the variables. And whatever you can try to think up what is a notion of equilibrium for this quantum state and measurements, it has to imply that this joint distribution here, these random variables are an equilibrium in the sense of Aumann, a classically correlated equilibrium. So we don't really gain anything there. And so what we have to do is we have to remember how we did it for the Bell inequalities. The non-local games, the players have to have an input that is kind of private to them. And then something happens. And so in Bayesian games, what happens is, this is kind of what they call games of incomplete information. Bayesian games, each player also has an input, so-called type, and they respond with an action. We assume a joint distribution of the types. They don't have to be independent generally, but often we assume that. And the payoffs for each player depend on the set of types and actions. So one way of interpreting this is that the players are playing some game which is determined by this vector t. But each player has only some kind of incomplete information which game is actually played. I mean, the payoff is determined by the full tuple of t's, but they can only respond to the ti that each player sees. So this is supposed to model certain things in markets, you know, in economic situations where players have sort of private information is correlated with others, objectives correlated with others, but anyway, this is for the economists. And so yeah, whatever the definition of strategy, they will again determine some kind of behavior like we've seen in the canonical games. And then we have a joint distribution of the types and the actions. And once we are there, then we can calculate expected payoffs. Yeah, so this is kind of how it goes. And so in a non-quantum world, this is actually not really that much more general than the previous one. Why? Because we simply have a different strategy space now. A strategy, what is that? If you're player I, you see Ti, and you respond with you see a type T, you respond with an action A. Well, that's a function, or at best a random function. Yeah, so we simply can apply the Nash framework to a game where the strategies are set of functions from Ti to AI. And but that's kind of okay. We can define mixed strategies for a player I. We can define correlated strategies as again a joint distribution of random functions. Whereas for the usual Nash strategy, it would be independent functions. And we can define equilibria in exactly the same way now, only that we now talk about the functions from type to actions. And so that's kind of, you know, the basic way we do it. For a quantum correlated equilibrium, okay, let's try this, how this would go. Quantum correlated equilibrium, we have Hilbert spaces for each of the players. We have a state on the product Hilbert space, and we have local measurements. And then we can define the behavior like we wrote before. This is the trace of rho times the tensor product of the measurement operators. This is a quantum equilibrium if for each player J and each alternative measurements that he can make. So then we can write an alternative behavior where the player J simply makes a different measurement. The expected payoff cannot increase. And so they doesn't affect the types, it just affects the distribution, the conditional distribution of their actions. So some observations is like these M's, we can always assume they are projective measurements. The rho, unlike non-local games, we cannot assume this to be pure. This might not actually preserve the equilibrium condition. We cannot just purify the state in some way. We recover classically correlated equilibria if all the measurements are diagonal in some fixed basis, and also the rho is diagonal in the same basis. And like this set of classically correlated equilibria, C, which is a convex polytope, also this set of quantum correlated equilibria, if I kind of take the union over all behaviors coming from some state rho in local measurements, that is also convex, even though the latter is not a polytope and also in general not closed. So these are sort of mathematical preliminaries. Let's forget about the belief invariant because I don't really have time. So quantum advantage, what would that be? Okay, so we want a game where we have quantum equilibria that beat every classically correlated equilibria, in the sense, for example, that it has a better social welfare. Yeah, just like we saw in the game of chicken, that the Nash equilibria lead to some social welfare, some total value. Thank you. And correlated equilibria correlation gives you slightly more. So so how would we do this? Well, we know such examples. I mean, that was my entry point. Non-local games where the players cooperate, that is a special case of the formalism here. I mean, nobody said that all the functions had to be different. I mean, it's actually crucial that they are arbitrary. Yeah, so if all the players cooperate, well, then obviously they have a common incentive to simply maximize U. So they implicitly cooperate. I mean, there are still more equilibria, but if I'm looking for the one with the largest social welfare, I just want to maximize the expectation value of some function, just like the CHSH game. And so what we know is that there are big separations we know that there are big separations between classical and quantum strategies and so on. So kind of, again, we wouldn't be here if we want to talk about non-local games in this old sense. There is actually something to do with cases when the players have different payoffs. So there is some kind of conflict. It's not a zero-sum game. That's kind of maximal conflict. But there is a long list, a long history of papers, starting with Pierfrancesco Lamour in 2005, and then 2015 and 16, a whole flood of papers looking at different ways of quantum advantage. And okay, so probably for this kind of talk, I don't really want to take the time to go through this example. So there, you can look at an example of basically, I mean, well, actually, I want to say this right now. All the examples are like this one. You start from a non-local game, for example, like the GLZ game for the that you play between 3 players. You have some kind of winning predicate here. Classically, you win with some probability. Quantum, you win with probability 1. It's actually very nice. And so this is like common interest. And then you just introduce a slight, tiny bit of conflict, which is here. We simply have 2 numbers, V0 and V1, and we attenuate each player's payoff. I mean, they have this winning predicate, and we attenuate this 0 or 1 by a factor, which depends on whether you say 0 or 1 as player I. So you have an incentive to say 1, but if you all say 1, you lose. So again, we have to avoid this. And so it leads to this kind of situation that the GLZ strategies are using the same maximum entangled state, and the local measurements leads to a quantum equilibrium with some payoff, where each player has this payoff, and the maximum social welfare of any classically correlated is this one here. And so the reason why this works is because, well, we have to check that this is still a quantum equilibrium, and they have slightly different objectives. So you have to check that just playing the GLZ strategy from the Greenberger, Horn, Seilinger paper is still an equilibrium, but that's your payoff then. How can we conclude that this welfare cannot be beaten? Well, the reasoning is as follows. The maximum you can get as a player I by responding is saying a 1, and then you get V of 1. That's the bigger of the 2 values. And we know that this here, the expectation of the capital V is only 3/4. You can only win 3 out of 4 of the cases. And so if you just sum if you just sum the payoffs and divide by 3, this is the GLZ inequality. You're just basically looking at, well, I mean, and the reasoning why we cannot get much more than this is basically because if we have a classically correlated strategy, well, then the behavior is classical. The behavior is a local hidden variable theory. And so I don't even have to use equilibrium here. And so I want to just go to this. I wrote this here again. Well, also that this can be applied to all sorts of different games. including the CHSH game. And yeah, so the criticism is all of those previous examples are basically just quantum non-locality in disguise. Thank you. We just constructed from a non-local game, and the payoff is just modified from the common payoff. And the quantum strategy is equal to the one that we had from the optimal violation of the Bell inequality. And then for the social welfare, this is actually just the Bell parameter. So we simply, instead of maximizing overall classically correlated equilibrium, we only say, well, all of those give rise to local behaviors, we just maximize over that. And that upper bound is enough to separate from the quantum payoff. So we actually just use the Bell inequality, which is kind of cheating. And this is probably why this whole direction hasn't really caught on. Today I want to show you another example. Hopefully I need not much more than 1 minute. This I call this CHSH for capitalists. So the market gives you an incentive to obey or violate Bell inequality. So the inputs are like this. It looks a bit like CHSH, but the types and the outputs are a bit modified. Alice doesn't have any input. It's a fixed thing, so there's no type. It's a trivial type. But she outputs both X and A. I mean, this is like the same X as in the CHSH game. Bob has the same Y input in the CHSH, and he outputs B, but he also puts out an X hat. And the idea is, well, they get a payoff if they win the CHSH game. So if A, X or B is equal to XY. But then they also play some kind of a zero-sum game where Bob gets a reward if X hat is equal to X, and he gets penalized if X hat is different from X, and Alice is vice versa. And so the intuition is that by introducing this zero-sum contribution, I mean, they both don't want that the other player can guess their private X, so they kind of have an incentive that those end up being independent and also uniform. Otherwise, each player can win. And then a classical strategy is essentially limited by the CHSH game. And so Alice, by not wanting to lose the second component of the game, she is sort of playing honest CHSH, even though she could choose X, and they could actually, I mean, they can violate the Bell inequality, but this wouldn't be an equilibrium. And then there's a quantum equilibrium, which is basically just using the maximum entangled state and has payoffs cos square pi over 8. So if epsilon is small, this is better than that. And I mean, this is even true for social welfare. If the sum of these is bounded by 3/2. And then the next idea, we can even do this with a separable state because Alice doesn't have an input. I mean, our strategy so far was, well, Alice, you pick X, then you measure your CHSH observer, which is just a sigma X and sigma Z measurement. Well, all of this can be folded into the advice, into the state. So instead of having the pure entangled state, we end up having a separable state where Alice gets the XA, Bob gets the X hat, all of them uniform. And then Bob, in addition, gets the post-measurement state. This is like the state after Alice applied something on her side of the maximum entangled state. And so this turns out is indeed a quantum correlated equilibrium with the same payoffs, cos square pi over 8. And this is in the paper that I'm saying. And so there are lots of different remarks about this. So one of them is that the resulting behavior that we get here is local. It's actually generated by local invariability. The reason is that Alice doesn't even have an input. This is a well-known fact. You can only have Bell inequalities if both players have a choice, not just one. So this is a local, this has a local invariability, but none of these gives a correlated equilibrium. This is kind of cool. As far as I know, that the economists, they didn't know this. They were talking about these behaviors and about convex decompositions, but this was apparently not known in an example. And so, yeah, this is like the conclusions. I mean, I don't know, I'm probably, if I talk a lot more, I'm just eating into the questions. Yeah, exactly. So I just leave it here, and yeah, I'm here for questions. There are plenty of open questions at this point, and probably you would know already some.
Many thanks for a very inspiring lecture. So maybe we have only 1 minute for one question. Are there any questions? So
not two.
Thank you very much for this interesting talk and bringing quantum to the game theory field. So is there also something like extended form games in quantum considered yet, where you have multiple rounds of games played? Like you said, there's a bridge, and I guess for the bridge game, you would have that. So extensive form games in quantum?
I mean, the mathematics is not different because they can always be brought in this form here. At least classically, right? So if you want to do this here, then it's different because in each step you would somehow have to do something repeatedly to the entangled state. So I haven't seen anything in this direction. So that, yeah, would be like, you know, basically the next thing to do, probably.
So unfortunately, we have to finish this lecture, and if you are interested, we can continue discussing in lunch break or coffee break. Thank you. Thanks the speaker again.